Bio-inspired algorithms is a topic that has interested me for some time now. The concept of observing the mechanics of nature and condensing them into formulas and rules that a computer can follow to solve a problem is very interesting to me. Ant colonies have been used as inspiration for ant colony optimization algorithms to solve problems such as the travelling salesman problem. Swarms of fish and birds have been used as the basis for algorithms such as particle swarm optimization, which solves optimization problems through swarm intelligence. Even bees have been used as inspiration to solve problems. Of course, not all bio-inspired algorithms have to solve a problem per se. Boids is an algorithm that takes inspiration from the flocking of birds and aims to replicate their behaviour. This algorithm is a simple yet powerful example of a bio-inspired algorithm that you've almost certainly seen before in games and movies where there are computer-generated swarms of creatures. Yep, if you've seen Batman Returns 1992, then you've seen Boids in action simulating swarms of bats. With this in mind, I wanted to give it a go for myself. A Boid simulation is made up of multiple agents, which in Craig Reynolds' original 1986 program were each designed to be a bird-like object, or Boid for short. The basis for the simulation relies on emergent behaviour arising from each Boid following a simple set of rules. Whilst the rule set could be expanded to incorporate any number of rules, the three fundamental rules for flocking behaviour are as follows. The separation rule will prevent Boids from getting too close and potentially clipping through each other, as well as determine how dense any emerging swarms will be. Conceptually, we're going to define a radius for which each Boid should endeavour to keep clear of other Boids. If another Boid enters this protected radius, the Boid should steer away from it until the offending Boid has left the protected area. Implementation wise, we're going to have to do a bit of setup before we can fully implement the rule. First, we need an array of Boids, each of which will contain its own displacement and velocity vectors. Then we're going to need to loop through every Boid, and for each Boid we consider, we're going to need to loop through every Boid again. If the Boid we're considering in the first loop is the same as the Boid we're considering in the second loop, we can skip this iteration. This way, for each Boid we consider in the first loop, we will compare it with every other Boid in the simulation by iterating through the second loop. We'll call the Boid in the first loop the considered Boid, and the Boid from the second loop the neighbouring Boid. Now we can implement the separation rule. In each iteration we can calculate the distance between the two Boids using some vector maths. If this is less than the predefined protected radius, then the neighbouring Boid must be in the considered Boid's protected range. Now we can steer away from this by calculating the vector that is directed from the neighbouring Boid to the considered Boid, and we'll call this the separation vector, and simply add it to the velocity vector of the considered Boid. Since we don't want our Boid to jerk away from its neighbour too quickly, we can normalise this vector and scale it by a scalar constant named separation sensitivity. Since this rule will be called every frame, scaling the vector will help to ensure that the Boids move away from its neighbours gradually, instead of increasing in velocity too little or too much each frame. Alternatively, we could just multiply by how deep into the protected zone the neighbour is as a percentage. This means that as the neighbour gets closer, the separation vector will grow linearly from 0 up to its normalised value, and the faster the Boid will move away from its neighbour. I found that this was often enough to smooth out the movement, however, exposing the parameter provided more versatility when trying to dial in exactly how I wanted the Boids to move. With the separation rule implemented, we need to do a small amount of work just to finish up. Firstly, we want to clamp the velocity between a specified minimum and maximum velocity to ensure that the Boids never move too fast or too slow to break the illusion of the simulation. Then we simply need to update each Boid's displacement by adding their velocity vector to their displacement vector, multiplied by the time between frames to ensure that they move smoothly and at the correct speed. We want to ensure our Boid's displacement vectors are incremented by their velocity vectors every real-world second, and therefore we only want them to move by their velocity scaled by the fraction of a second that occurred between frames being displayed. For example, if a Boid moved at velocity 2.5 and the time between frames was 0.1 seconds, we would only expect the Boid to be displaced by 0.2-0.5 rather than the full 2.5. After 10 frames, 1 second would have elapsed and the Boid would have been displaced by 2.5. Lastly, we'll also want to update the Boid's rotation here to ensure that it rotates smoothly towards its velocity vector. This will make sure that the Boid always turns to face the direction it's moving in. All of this provides us with our basic movement implementation and our first rule. This rule is fairly obvious to see already, but I wanted to add some visualization tools, so I added in the radius to be drawn around each Boid. I was really happy with the outcome so far, as we already had some pretty smooth and convincing motion from the Boids from the first rule alone. The alignment rule is where we really start to see the flocking behaviour of the Boids, as this rule aims to steer Boids that are close to each other in the same direction, which ultimately forms a flock. The first thing we need to do for this rule is to define a visibility radius for the Boid, just like we defined a protected radius in the previous rule. This radius will be used to determine if another Boid is visible to the current Boid, and if it should be considered as part of the current Boid's flock. If the neighbour is within the visible range, then the current Boid can see it and will consider it part of the flock and include it in its calculations. If the neighbour is outside of this range, then it will be ignored by the current Boid. Now, for all neighbours that are considered part of the flock, we will need to average their velocities to get an average velocity for the surrounding flock. Then we can calculate the vector from the current Boid's velocity to the average flock velocity and multiply this by an alignment sensitivity constant, similar to how we did in the previous rule. We can then add this to the Boid's current velocity to steer it towards the average velocity of the flock. This provides us with an effect where voids that are close enough to each other will appear to steer together in formation. In addition, since each void is influenced by only the voids in its visible range, it also provides an opportunity for voids to move away from their current flock if enough voids from another flock moving in a different direction enters the current void's visible radius. The cohesion rule is more subtle than the previous rules, but essentially its goal is to steer the voids towards the average position of their surrounding flock in order to keep the flock together. Since we've implemented the previous two rules already, this rule is very simple to add. We're simply going to average the position of each neighbouring void that is in the current void's visible range, and then calculate the vector from the current void's position to the average flock position. We can then scale this by a cohesion sensitivity constant and add it to the current void's velocity in order to steer it towards the average position of the flock. This helps to ensure the voids don't drift apart from each other when part of a larger flock, and it's much easier to see its effect when compared side by side with voids that don't use it. Putting it all together, we've achieved a nice result. At this point, I should point out that for simplicity I've demonstrated this in a single method. However, given the rule-based nature of this simulation, I'm going to go ahead and refactor each rule into a different method, for clarity and ease of expansion. In this completed implementation, we can try some different parameter values to see how they change the result, and ultimately fine-tune the movement of our voids. Seeing these changes in real time can give us a better understanding of the effect each parameter has on the simulation. Moving this into 3D uses exactly the same code, except our velocities and positions are 3-dimensional vectors, giving us an extra z-axis, but this is all accounted for in our vector maths. Now that we're working in 3 dimensions, we can spend some time focusing on improving the look of the voids. First, we can add better 3D models for the voids, such as this fish model. Of course, these look a little bit static, so we can also add some animation to breathe some more life into our fish. That looks much better, but it's still missing something. Our fish probably shouldn't be swimming in a void, so we can add an environment to further sell the effect. Now our fish look much more at home. So far this looks great and our voids work well, but not without some issues. There are still a couple of things this implementation doesn't account for that we should probably fix. Firstly, collisions. With a bit of vector maths, we can handle collision avoidance between a given void and the environment at the expense of some more compute time each frame. The first issue that needed to be handled was actually detecting that a collision was about to occur. Since I'm using Unity, I can make use of the raycasting functionality to essentially look ahead in time. For this, we'll assume that the void is going to continue at its current velocity. This probably won't be true since it will be influenced by neighbouring voids every frame, but in the current frame we need the voids to respond to a potential collision as if it were going to happen, since the void doesn't look ahead to see how its velocity will be changed by surrounding voids, and therefore we can't assume the collision won't happen. Therefore, we'll raycast forward a small amount in the direction of the void's current velocity. If a collision is made with an object or piece of terrain, then we can get the location of this potential collision site and alter the void's velocity to try and avoid the collision. My initial attempt at collision avoidance was to simply slowly reverse the void's velocity so that it would reduce its speed as it reached the obstacle and then move back in the direction that it came from. This didn't provide a particularly convincing motion and often resulted in voids stopping completely at the point of collision, successfully avoiding the collision, but not actually continuing to move. Eventually I settled on the much more sensible idea of gradually reflecting the void's velocity, so that it would swim up to and away from the collision point smoothly, in a way that seemed to naturally continue the initial direction of the void. This was achieved with some vector maths to calculate a reflection of the void's velocity vector on the collision surface, given the normal vector to the point of collision. A few calculations later and we arrive at this equation, which gives us the reflected velocity vector. Of course, many maths libraries probably include a built-in method for this. In fact, Unity actually does provide a method for this, so we can change our code to use that instead. We can then use a similar implementation to the avoidance rule by slowly adding a scaled version of the reflected vector to the current velocity, to smooth out the change in velocity over time. But this time we needed the scale of the velocity change to be inversely proportional to the distance between the potential collision and the void. So we take the unit vector of the reflected vector, and multiply it by 1 over the distance to the collision point, and then multiply it by the magnitude of the void's velocity. Since we're altering the velocity again, we'll also want to move our speed clamping code so that it's performed after collision avoidance. Multiplying by 1 over the distance meant that if a void detected a potential collision relatively far away, it would only adjust its velocity slightly. If this was enough to avoid the collision, it might not even be noticeable that the velocity was adjusted. If the void kept approaching potential collisions with a decreasing distance between itself and the collision, the velocity change would become more drastic each frame until eventually the void had a velocity that would move it away from the collision, or the void's angle of approach was changed to the point that it became parallel with the surface of collision. In more mathematical terms, since 1 over the distance between the void and the collision point should tend to infinity as the void moves closer, so too will the magnitude of the reflected velocity that is added to the void's current velocity. Whilst multiplying by 1 over the distance to the collision point helps us to ensure a void moves away from a potential collision, multiplying by the magnitude of the void's current velocity helps provide us with smoother, more natural movement for voids moving at higher speeds. Essentially, faster moving voids will change their velocity faster than slower moving ones, as higher magnitude velocity vectors will linearly increase the magnitude of the reflected velocity that is added each frame. The final result of this collision avoidance was very effective and didn't noticeably disrupt the intentions of the void, but instead provided a motion that seemed almost pre-planned, which is exactly what we were looking for. At this point, before moving on to fix further problems with the current implementation, I wanted to test the idea of adding a sort of personality to the voids. The idea being that since different parameter values can provide different behaviours for the voids, we can easily create voids that have different behaviours by supplying random values for these parameters. Curious about how this would play out, I went ahead and gave each void its own parameters, randomised their values between some sensible predetermined ranges, and played the simulation. In the first few attempts at this, there were only a handful of voids, and nothing particularly interesting happened. Increasing the number of voids in subsequent attempts showed promise, but it was obvious that some of the ranges for the parameters were not particularly appropriate. In this final version, the parameters were tweaked to reduce the amount of overlapping between voids. However, it was still not perfect as some of the voids seemed a fair bit twitchy. Nevertheless, this larger simulation with more appropriate parameter ranges shows the interesting effects of having voids with different parameters. The flocks were much more dynamic, forming and disbanding much more easily. The distribution of voids was also much less uniform within the flocks. There were now areas of high and low densities. Overall, the simulation was simply more unpredictable and lively. This was especially obvious when directly comparing this simulation with another simulation that used the same parameter values for all voids. This provided quite a striking contrast between the uniformity of the simulation using global parameter values and the liveliness of the simulation using unique parameter values for each void. However, it's important to note that neither is particularly better than the other, since it really just depends on how you want your voids to act. Whilst this was an interesting tangent with a fairly pleasing result, I decided to stay with the use of global parameters for now. Now, of course, our simulation looks very appealing, but like myself, you've probably also realised the limitation of this implementation a while ago. And you probably realised it at the same time I did as well. Then we're going to need to loop through every void, and for each void we consider, we're going to need to loop through every void again. It is very apparent that this is an ON squared algorithm running every frame, so we should probably parallelize it. If we were working with a thread-safe framework, it's simple to see how this could be parallelized. Each void makes its own calculations for its velocity change, which are completely independent of every other void's calculations. Therefore, this could easily be threaded and performed in parallel to reduce calculation times with large numbers of voids. Similarly, updating each void's rotation and checking for collisions are also completely independent, and therefore could be parallelized. Where we run into a slight challenge is when we update each void's position and velocity. We shouldn't update either of these in parallel with the velocity calculations, as it would mean that voids in different threads might be calculating their velocity based partially off velocities and positions from the previous frame, and partially off ones from the current frame, meaning that the simulation is at the mercy of multiple race conditions. Whilst this might not have a massive impact visually, it is technically incorrect, so we'll avoid it. On the other hand, updating each void's velocity, position and rotation should be parallelized, since each void's update is independent of every other void's update. They just need to be performed after all velocity calculation threads have completed. Since I'm using Unity, updates to object transforms and raycasting are not thread safe, and so I'll only really be able to parallelize the velocity calculations, since parallelizing the small amount of thread-safe code in the velocity and position updates probably wouldn't provide any benefit. With this in mind, the final parallelization code creates an array of threads each frame and distributes voids evenly to each thread. These are then started all at the same time, and when all of them have completed execution, we proceed to the serial transform updates as normal. Using threads helps speed up the implementation significantly. Running a simulation of 3072 voids in serial provided us an average execution time of the simulation code per frame of 293.69 milliseconds. At best, we were able to achieve a speed of 8.38 times the serial implementation on 64 threads, at an average execution time of 35.03 milliseconds per frame. Tuning it slightly for the CPU running the simulation, we managed to squeeze a little bit more performance out of it, giving us an 8.56 times speed up at an average execution time of 34.32 milliseconds per frame on 24 threads. Sadly, this isn't a particularly efficient solution at only 35.7% efficiency, although it's worth noting that the theoretical maximum efficiency on 24 cores is 55.4%, only 19.8% more than what we achieved. To achieve better results all round, we'd probably need to rework the inner loop where we check which voids are in range. This seems like a prime candidate for spatial partitioning, which I'm interested in learning more about and perhaps applying it in a future video. In the meantime, rather than spinning up new threads every frame, we can reuse the same threads by using a thread pool. This provided a small boost in speed, but it was nothing particularly significant. After some measurements using the serial version, I found that the percentage of execution time spent in the velocity calculations, which can be parallelized, is about 96.5%, and the percentage of time spent in the transform updates, which have to remain serial, is about 3.5%. Using this, we can calculate some theoretical maximums for the speedup on each number of processes using Amdahl's law. If we compare these theoretical speedups to the observed speedups, we can see that we follow them reasonably closely up until the CPU's logical processor limit of 24. An interesting alternative approach would be to use compute shaders so that we can utilise the power of the GPU when parallelizing the simulation. So I translated our velocity calculation code to HLSL so that we can run it on a GPU. This provided a significant increase in speed compared to the CPU implementation. Again, with 3072 voids, we managed to achieve an average execution time of 24 milliseconds, of which the parallel velocity calculations take only 13 milliseconds to complete, which is around twice as fast as the best CPU result. Of course, if we didn't need to run this in real time, such as if we were pre-rendering a shot for a movie, we can get up to 30,720 voids, specify a constant delta time such as 1/24 for a 24 frames per second scene, and then limit the simulation to a much slower frame rate, capturing each frame for playback later at 24 frames per second. This is actually exactly what I did for the footage that's on screen currently. This was looking good and I was pleased with our speed increases, but there was one last thing I wanted to add just to make the simulation a bit more interesting, and that was a predator void. There's a number of different ways you could implement this and definitely more detail that could be added, but I used a simple approach of defining a type for the void and then performing different velocity calculations based on these types. If the types of two voids matched, they would flock like normal voids. If a predator type void was assessing a neighbour void that was a prey type, they would calculate a separation vector and add this to their velocity so that they can move towards the prey. Conversely, if a prey type void was assessing a predator type void, it would calculate the same separation vector and add this to their velocity in order to move away from the predator. This provided a simple yet effective way of having the predators chase the prey and have the prey try to escape the predator. It also provided a way to have each type flock only with members of its own type, and this provided some pretty interesting behaviour. And there we have it, a complete void simulation. This was a fun project to work on and I'm happy to leave it here. As always, there's plenty extra that could be added, and I hope that if I have time in the future I can come back to this project and implement a few of them. For now though, thanks for watching.